to section 1.4 of Anton about inverses and algebraic properties. So again, matrix multiplication is the most important operation involving matrices. And well, the good news is it is associative. In other words, if you multiply A times B first, compute the product of those matrices, and then multiply by C, that's going to equal A times the product of B and C. Provided the matrices are all of the appropriate sizes, so multiplication is defined. But matrix multiplication is not commutative. Okay, so in other words, that means A times B does not necessarily equal B times A. I mean, in some cases it will, but generally speaking it won't. And here's actually quite a simple example. If A is a 2 by 3 matrix and B is a 3 by 2 matrix, then the product A times B is going to be, you take the outside number here, the outside number here, and so A times B is going to be a 2 by 2 matrix. Whereas B times A, so again, B is a 3 by 2 matrix. I haven't chosen any specific example, but this holds in general. And then A is a 2 by 3 matrix. We can multiply them because the interior numbers match up, and the result is going to be the numbers listed out here, a 3 by 3 matrix. And so A times B can't equal possibly B times A, because A times B is a 2 by 2 matrix, and B times A is a 3 by 3 matrix. And so they're not even of the same sizes, so they can't be equal. Okay. Then moving on to the identity matrix. This is going to be an important matrix. It's simply the matrix where you've got ones along the diagonals and zeros elsewhere. So I didn't bother writing the zeros. This is an n by n matrix and it's denoted I sub n. So for example, the 2 by 2 identity matrix, I sub 2, has ones along the diagonals and zeros elsewhere. The 3 by 3 identity matrix has ones along the diagonals and zeros elsewhere. The reason it's called the identity matrix is that if you take any n by n matrix A and multiply by the identity on the left or by the identity on the right, you're going to get the original other matrix you started with. So here's a 2 by 2 example. Here's a 2 by 2 identity matrix. Here's some random arbitrary 2 by 2 matrix. Then again, matrix multiplication is a bit funny. It's not component-wise. So the B here is not simply 0 times B. No. You have to do this thing about the dot products. So the entry here this is in the 1, 1 position. So you take row 1, column 1, and dot them. In other words, 1 times A plus 0 times C. And that gives me this A. To get the B here, you take, this B is in the row 1, column 2 position. So I take row 1, column 2, dot them. So 1 times B plus 0 times D. So that's how we get this B. Okay. Anyway, so the point is that we started with this matrix and we get the same matrix again when we multiply by this identity matrix. So this is going to come up in a few sections, this identity matrix. Okay, if A is an n by n matrix, an inverse of A is another n by n matrix, I'm going to call it, or denote it A to the minus 1, such that A times A inverse is the identity matrix, and A inverse times A is equal to the identity matrix as well. Now, a matrix, an n by n matrix, may or may not have an inverse, and it's an important question of when it does, and we'll find a very useful and easy answer. Now here's the formula for the inverse of a 2 by 2 matrix. So remember, a 2 by 2 matrix has this 2 rows, 2 columns, so here's the general form of it. And then I'm telling you that there's a simple formula, or well, it's somewhat simple, is that the inverse, A to the minus 1, is given by this expression here. So this delta is the determinant. That's given by A times D minus B times C. And then to find the inverse, what you do is take the diagonal terms here, a and d, flip them, so it becomes d and a, and then tack on minus signs onto the the off diagonal is what it's called, and then divide every term by the determinant. So that's what's the scalar multiplication, if you recall, is taking the scalar out here and multiplying every term, in this case dividing by delta, every term by delta. So that's what we see here. Now for 3 by 3 matrices, there's not such I mean, there is a formula, but it's not so easy. Here's an example of a 2 by 2 matrix, and we find its inverse. So the formula says to find A inverse, you take the original diagonal, flip it. So 8, 1 becomes 1, 8. Tack on minus signs onto the off diagonal terms, and then divide every entry by the determinant. So the determinant is the product of the diagonals, the diagonal terms, so it's 8 and 1, minus the product of the off diagonals, so 2 and 5 is 10. So our determinant is minus 2. So we want to divide every single entry by minus 2. So 1 divided by negative 2 is negative 1/2, and so on. So 8 divided by negative 2 is negative 4. And so this A inverse is given by this matrix. And again, if you did the multiplication, take this matrix A, this matrix that we found, and multiply them together, you'll get the 2 by 2 identity matrix with 1s along the diagonals and 0 elsewhere. Let's explain why that formula for A inverse works. Again, only in the 2 by 2 case is where that formula applies. So again, we've got A is equal to A, B, C, D, and then I'm asserting that the inverse is equal to 1 over the discriminant. I flip the diagonal terms, tack on minus signs on the off diagonal terms. Okay, so A times A inverse is going to equal A, B, C, D times 1 over this delta times D minus C minus B, A. And it's a fact that you can move a scalar around out over here. So let me do that. That's a bit sloppy. Okay, so then to multiply these two 2 by 2 matrices, because this is a 2 by 2 and this is a 2 by 2, I can multiply them because the inner numbers match, and the result I'm going to get is a 2 by 2 matrix, and so I need to make space for a 2 by 2 matrix. And so, okay, so the entry in the 1, 1 position here, it's not going to be 0, or it might, well, it's not going to be 0, but I need to take row 1 and column 1 and take their dot product. So that's going to be AD minus BC. Why? Because A times D plus B times negative C. So that's how I got this. Then let's figure out the entry in the row 1, column 2 position. So I need to take row 1 here, dot it with column 2 there. So A times negative B plus B times A, that's going to be, well, I'll write it out here. So minus AB plus BA, but you see that that's going to be 0. Similarly, in the row 2, column 1 position, I take row 2 and column 1 here, take their dot product, so that's CD minus DC. That's going to turn into 0, just like this one here is 0. And then finally, in this spot here, this is the row 2, column 2, so I take row 2, column 2, dot them. So that's negative BC plus AD. Okay, and let's simplify these terms. So AD minus BC is the discriminant delta, or determinant, sorry. This is a 0, this is a 0, and here we have AD minus BC, which is the determinant. And then finally, when you do scalar multiplication, you multiply every single entry by that scalar. In this case, we're dividing by delta, and so this becomes delta over delta, 0 over delta, which is 0, 0 over delta, and delta over delta. And this is 1, 1, 0, 0, which is the 2 by 2 identity matrix. And so what we figured out is A times A inverse is equal to I2, which is the what we wanted. And then similarly, one could check, I won't do it here, but A inverse times A is the identity matrix as well.